So we'll focus now on a technique that we're going to learn on how to solve inequalities with a polynomial, like the one I have up here. So that means I have a polynomial on the left, greater than a number, or less than a number, and it could be greater than or equal, or less than or equal. So we might not have a lot of experience of what higher degree polynomials look like, but at least for quadratics, we know these are parabolas, right? So what do the graphs of these look like? That's what we are going to be focusing on. And the main idea that we're going to work is that we're going to think of the graphs. We might learn more carefully about the graphs of these functions, of these equations for us so now. But the idea for us is going to be the following, that the main idea is that the graph of the polynomial, so I'm calling p of x a polynomial. So if I graph y equals p of x, the graph can only change from negative to positive. That means to being below the x-axis to above the x-axis. Only it's going to cross there from points where it intersects the x-axis, right? So if you understand what I'm saying, is I'm saying that this is going to be your xy coordinate system. If you had a parabola, it's going to look something like this. So the value of the polynomial here is positive, but then it's negative in this section, and it's positive again. And it changed from positive to negative through these points, right? So that's as simple as that, and that's going to give us the idea of how to solve this. So let me show you here in Desmos. I have a few polynomials to share. The first one is a very simple parabola. This one, if you try to solve this one equal to 0, you would have no solutions. So this one would have nowhere where it crosses the x-axis. But if I change the value here to a minus, then you have two x-intercepts. And we're going to say that this part of the graph here, under, right, from here to here, these are the y values that make it negative. Sorry, the y value is negative, so the x values are making this negative. While for all the values, for these values of x, the y is positive, right? So if I have to solve the inequality, this polynomial being greater than 0, it would be for all the regions over here, from here to here, and not between here and here, not between -1 and 2, but then again from two positive values of x. I have another polynomial here. This is a cubic, and it has the same behavior in the sense that if the graph is below the x-axis, if we could find these points where it's 0 here, here, and here, then we know where it's going to be below the x-axis, above, below, above. Now, something could happen as well. I have here, the next one I don't have it written as a polynomial or not expanded. But of course, you can know that if I work this out, this first part would give me x squared minus 4x plus 4. Multiply that trinomial by x plus 3, and you get a polynomial of degree 3, right? Another cubic. I divided by 12 because that will shrink the graph a little bit. We'll see that later when we see functions, what that 12 is doing to it. But this is something that's different happening here. See, this is 0 when x is 2. We'll make this factor equal to 0. But because it's squared, you have like a double. Yeah, it's not crossing the x-axis. It's just touching it and bouncing back off. So for that reason, it's not as simple as find where it's equal to 0 and then check it's above, below. We have to do a little bit more careful looking at if it's going to bounce off like here. But the method we're going to use for this section, at least, is going to be much more simple now. We're not going to have to worry about this because we're going to be doing is the following. We're going to be doing how are we going to solve an inequality of this form? Well, first of all, it's not going to be like the one I had. The one I had greater or equal than 10, and I'm not going to solve it with a number on that side. The first thing to think about is like when we're solving quadratics, we want to move this to the other side, and we would have x squared minus 6x minus 4 greater than 0, right? That's the one we would be working on. So we would have a different polynomial on that side, and solving this one is equivalent to solving the other one greater than -4. Greater than 0. So when you have that, you're going to check where's the binomial, the trinomial, the polynomial in this case, equal to 0. So what that means is if you're going to have your x-axis and you find your zeros, and this is like your first and your second solution, if it's a parabola, it's kind of simple. Our experience tells us that this parabola, if the a is positive, is going to open like that. If the a were negative, it will be open like that. right? So we have an idea already where it's going to be positive, where it's going to be negative. But if it's a cubic or a bigger, higher degree, we might not know. And just because this technique will work for later, what we're going to be doing is cut the x-axis into regions cut off by those segments. What does that mean? This is going to become my region 1. This is going to be my region 2, between x1 and x2. This is going to be my region 3. Yeah. Then you test after that, let me copy this to bring it with me. Then you're going to check a point within each region. So what I mean by that is you're going to check a point to the left of x1, whatever point you want. You're going to check a point between x1 and x2, and you're going to check a point between after x2 in this case. Yeah. If your sign is positive, then you know you're up here. If your sign is negative, all you care is evaluate the function in that point and then check if it's positive or negative. If it's negative, you know you're under here. It's positive, it's over here. So something like this will give you that graphically, this thing that the graph of this parabola would look like that. Right? It's positive, negative, positive. Sorry, I'm in the way here for my third positive. Okay. So if you do that, then we have all the information. If I want to solve where is this less than 0, I know it's for all numbers here. Right? It cannot become, if I know it's negative here at the point where I tried it, and I know it cannot change to positive until it crosses through these points, right? So it's that's saying that for all values in here, it's going to be negative, right? So that's how we solve it. So at the end, we say one last thing. Let me again copy this and bring it with me. So the last thing we're going to do is list the regions as the solutions of the inequality, the regions that match that. Okay. So okay, let's do this in a simple example to wrap these things up. So let me see. My first example is this one: x squared minus 6x plus 8 less than or equal to 0. So my step 1 was solve the equality. Okay, I'm not going to solve with an equal sign. Sorry, with an inequality. I'm going to solve with the equal sign. So I'm going to find where is that parabola or this equation equal to 0. So you solve it as you know how to do that from the past. If I want to solve this, okay, I put the equal sign. And this one, I believe we can factor. It's x minus 4, x minus 2. That means that this is 0. Why? Because multiplied negative 4 and negative 2 gives me a positive 8. Added gives you a negative 6. So now that means that x is 0 either when this is 0 or when the other factor is 0. This gives me that when x is 4. This gives me that 0 when x is 2. So what I do now is check my regions in these pieces. I'm going to just put some colors here. So this is my region 1 before the 2. The second region is between the 2 and the 4. And my third region is going to be after the 4. Okay? So pick any number in the first region, in this case in my green region. So I'm going to check. So I'm going to evaluate, I'm going to write here something like this, like at x equals 0, I'm going to pick that value here. Okay, for the green, I'm going to pick at x equals 1 for my second region. I'm going to pick at x equals 5 for my third region. Let me color code this to make it clear what's happening. So this is my region, the blue region. This is my point for my green region. This is my point for my orange region. Okay, and just evaluate the function, evaluate the equation. I'm using language of the next section. Equation at this point. So at 0, if I plug in 0 for x, I'm plugging it in here. Right? So at 0, that will give me a positive 8. So at 0, this is positive. I'm going to do 0 squared minus 6 times 0 plus 8 is 8. So it's positive. At 1, you can evaluate it here or in the factored form, right? The factored form might be even easier if you want to do it because it's easier to plug in the 1 there. Let me do it there. If I plug it in the factored version, I'm going to get a 1 minus 4 is a negative 3. So I can do it. Sorry, I'm doing both times. 1 minus 4 and 1 minus 2. This gives me a negative 3 minus plugging in a 1, 1 minus 4, and 1 minus 2. Oh, sorry, I'm plugging in a 1. The 1 is a bad point. I hope you noticed that. That's why I was like, what? I cannot plug in a 1 here. The 1 is still in the same region, right? The 1 is still in the same region right there. So maybe you caught that when I was doing it. No, I had to plug in a number between the 2 and the 4. So I need to plug in something like the 3. Sometimes we have to use decimals, right? A fraction, but in case I can pick a 3. Okay, so let's pick a 3 now. Now I can do it 3 minus 4 and 3 minus 2. I'm evaluating here in this expression. You could do it in either one, right? These are the same in that form or in the factored form. I'm using the factored form on this one. So plug in a 3, I get 3 minus 4, that's a negative 1. And 3 minus 2 is a positive 1. So that gives me a negative sign. I don't care about the number, it's a negative 1, but I care about the negative. And then the last one, I think I'm going to get a positive, of course, but let's check. I'm going to get 5 minus 4 times 5 minus 2. So I get a 1 times a 3. So it's a 3. So it's a positive. Okay? So there you go. I got my 3 regions. I evaluated the points. I wanted to check where it was less than or equal to 0. Okay? And that's in this region, right? In my region number 2. So because it says less than or equal, it includes the endpoints. So my solution is the interval from 2 to 4, including the endpoints. Okay, now you might ask yourselves, well, why do we go out through this process if I could just graph it in Desmos and see the parabola, or and for any more complicated things in the parabola? That is true, but we need students to be able to solve these kind of situations without the aid of technology. And on the other hand, this is going to be a technique that's going to be very useful for taking care of things later in calculus when we use something called the first derivative test. So this is very simple. It might feel like we're working too much, but it really is to get an idea of the techniques we're going to be using later in our later courses. For a parabola, it might be so simple. And again, if you're used to graphing a parabola, this would be a parabola. We know it's going to look like that. Right, if I graph like this, so you can answer it from there. But the technique is what is important for us right now to practice this.